Hello. It's fine. Okay. Still not spent. So I hope the screen is visible to you. My PowerPoint, I hope it is visible to you. And if I'm audible, please type your attendance there in the chat box. I will record this attendance also, just for the sake of it. But if there is a genuine problem with some students, I can consider their attendance. Okay. So this was the problem we discussed. Uh, we considered this region bounded by the three surface. The first surface is infinite cylinder along the z-axis having radius 2. That is, the equation of that infinite cylinder is x squared plus y squared equal to 2. And the bottom of another surface which bounds the considered volume here, the V volume in this uh, divergence theorem is z equal to 0 surface. Z equal to 0 surface, as I discussed, it's a flat surface on xy plane, so that for every surface, that is S1 here, for every point on the surface, z value is 0. And another flat surface we consider is z equal to 3. So we consider a flat surface which intersects the z-axis at 90 degree, so that for every point on on such flat surface, that value is 3. So we have one flat surface on top, another flat surface on bottom, and which cuts the infinite cylinder into this type of cylindrical box, right? So this is the cylindrical box that we consider. And here, in order to verify the divergence theorem, which states that the volume integration of divergence of the vector field, which measures either the net outflow or the net inflow of the vector field over the whole volume, equals the total flux, or a measure of the total number of vector field passing through the surface S. The total number of vector field passing, it's a measure of the total number of vector field A passing through the whole enclosed surface, right? So this is what we have to prove. And for that, we start with the left-hand side here. And for the left-hand side, we calculate divergence of A and do this volume integration and all, considering the volume element as dx, dy, and dz, because we are considering Cartesian system, x, y, z coordinate system. And for the right-hand side, we have considered, as we discussed at the very beginning, we have considered three surfaces. One surface S1, another surface S2 here, and another surface S3, which is the curved cylindrical surface. And we have calculated the flux over this surface and found out to be 0. And again, we calculate the flux over this surface and obtain this to be 36 pi. All right. Now our next calculation is to calculate the flux over this curved cylindrical surface, the curved surface over here as represented here. So in order to consider this integration over the curved surface, what we need to find out is we need to find, in order to perform the integration, this is x, this is y, this is z. In order to perform integration over this uh, curved surface, the curved surface here. I can see that. I hope that you can consider a curved surface. So in order to perform a surface integration over this curved surface, we need to find a surface element on the curved surface. Okay, we need to find a surface element on the curved surface. So let's say we consider infinitesimally small element. This, we consider this as a DS3 surface element. And if we write surface element vector DS3, that will be outward unit vector into magnitude of this DS3 that we discussed today. And that will give you an outward unit normal vector, something like this, n cap. All right. So at any point on the curved surface, we can consider the common surface element. So over here on this flat surface, we have said that this surface is lying parallel to the XYZ. So you consider any area element here. You consider any area element here, infinitesimally small area like this. So this can be considered like this to be a small increment along X, and this to be a small increment along Y. So this area element will be this ds2 is area element is dx dy. And similarly over this flat surface, to consider any area element here, this area element, this along this, what I highlighted here, it's your increment along small increment, small segment along x-axis, and this side is equivalent to small segment along y-axis. So this area element is dx dy. So the surface element ds1 is here also is dx dy. Okay, if it lies on the xy plane, if the surface is parallel to the xy plane, so the surface element you can write it as dx dy. Similarly, if you consider any surface, let's say this is x, this is y, this is z. If you consider any surface, something like this, parallel to the yz plane, this is your yz plane, right? So if you consider any surface parallel to the yz plane, the surface element here in this case will be considered a small, infinitesimally small rectangular box. So this segment here is dz, this segment here is dy. See, this axis is y, this axis is z, right? So the area element here in this case will be ds will be dy dz. So accordingly you can choose for a flat surface the area element. All right, now for this curved surface, how are we going to choose the area element ds3? So that I think you can picture from here. So if you draw like a line here where this intersects this and this like this, so this is your x-axis, right? This is your x-axis. So the angle subtended by one edge here, we call it theta, and the angle subtended by the other edge of this small area element, we call it this angle as small increment theta, theta plus d theta. That means the angle here over here will be your d theta. I hope you can understand that. And the radius of this circle, what is the radius of this circle? 2, right? We have considered this area x squared plus y squared equal to 4. So the radius of this circle is 2. So from here to here it is 2. From here to here it is 2. Okay, so you see that in order to consider this area element here, along this, if you look at this, the one I highlighted here, it is along here also. It is along z-axis, isn't it? What I highlighted here is along the z-axis. This edge is small changes along z-axis, or small line segment along the z-axis. So this is dz. That is known to us. But what about this curved surface? There is a curved surface here, a curve, not curved surface, there is a curved line here. So for that, let us just look at this way. So I hope you can see that. So this is your dz, and let me redraw it again because I have made it very messy, that picture. So I think I have drawn this cylinder probably for the 4th or the 5th time, I don't remember. So anyway, so we are going to consider a curve, some surface here. on the curved surface. So we can see that this will be curved, and but this being the z exists, so this small segment here, this side will be dz, infinitesimally small segment along the z-axis. But in order to find this segment, the area of this will be, let's say this segment, this curved line is, let's say dl. So area ds3 will be dl into dz. All right, dl into dz. So what is dl? In order to find dl, what we are going to do here is this: we consider it as a, we consider this as a theta, and we consider this as a d theta. That's what we do, right? So if this is the picture, okay, the picture. So the radius here is 2. I hope you can see the picture I redraw here. So this side is your dz. Now, now if you take a tan d theta here, tan d theta, it's like, if you consider to be infinitesimally small segment here, in a small angle approximation, if d theta is very, very small, see, let me redraw something like this, if this angle is large, if this d theta is large, so this angle is quite acute, right? It might be around here is, let's say 75 degree or something like that. If this angle is smaller, if d theta is smaller, this angle will now become, let's say this is probably around 85 something. But if you make this angle to be very, 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 very small, something like this, very, very small angle, this d theta is very small angle. So if you consider this angle here or this angle here, they are approximately 90 degree. They are close to 90 degree. Okay. So because of that, you can consider this as a right angle triangle. Right angle triangle. One of the angle, you just assume it as a 90 degree. So this is as 90 degree for a small angle d theta here. This you can consider as a right angle triangle. So if you consider this as a right angle triangle, tan d theta will be opposite. Opposite here is your dl, and adjacent here is the radius of the circle. So opposite is dl, adjacent is 2. Opposite side upon adjacent side, dl upon 2. And there is this thing called Taylor series expansion, which you will probably study in mathematics. Taylor series expansion in physics also, I think Sir Guru will teach you. Taylor series expansion, which says that tan theta is equal to theta minus what is that? Theta square upon 2 factorial plus theta cube upon 3 factorial, something like that. I don't remember exactly. Theta to the power 4 upon 4 factorial. So if this angle theta is small, this is very small. Let's say your theta is 0.01 degree. If your theta is 0.01 degree, what is theta square? Theta square will be 0.001201 degree, right? So if you take theta to be very small, the higher order term, theta square, theta cube, theta 4 term, they will become very, very small. What will be theta cube? Theta cube will be, if you take 0.01 to the power 3, this will be 0.0000001234, this, right? So this theta cube term, theta square term, theta to the power 4 term, they are very small, so they can be negligible for small angle approximation. So there are two things. If this angle is small, you can consider tan theta to be equivalent to theta. And also, if this angle is very small, the angles subtended here, they are very close to 90 degrees. So you can consider that one of them or both of them as a 90 degree, and then you can consider a right angle triangle, and then you can consider a trigonometry, which says that tan d theta is equal to opposite by adjacent. Opposite here is your dl upon adjacent. The side of this triangle is 2, the radius of a circle. Okay, so this is what we do here. Tan d theta is equal to, this is your here as I represented here, dl upon the radius is 2. And for small angular approximation, for small d theta, for small increment here, tan d theta is equal to d theta, because higher order terms are 0, as I explained before, d theta dl upon 2. So your dl is 2 d theta. Then your ds3 will be 2 d theta dz. Right. So that is your surface element ds3. Now, like again from trigonometry, if this is your x-axis, this is your radius r, this is your radius r, this x coordinates over here, x can be written as r cos theta. Okay, if you drop a perpendicular here, this is so messy again. Just for the last time, I will not draw again. X, Y, Z. So this is the first thing I think we discussed. So I need to take a little bit more time. The rest of the integration, you can do it. So let's say this is your x parallel to x-axis, and let's say this is your this thing, right? So you drop a perpendicular here to this x-axis. So let's say this is 90 degree. So the x coordinate value is this. So this will be, if this is the radius of the circle, and this is your angle theta here. This is your angle theta here. So from this you can write x as r cos theta. And if you drop a perpendicular, this is the y-axis. If you draw a perpendicular, this y here, this is 90 degree. So you can write y as r sine theta. So I hope you are familiar with that. So you can just picture a right angle triangle there, and then you can write x as r cos theta and y as r sine theta. So like this, you write x in terms of theta and y in terms of theta. Here the radius is 2. Instead of r, you just put 2. Okay. So when we do that, and also in order to find the normal to the surface here, so as I have explained before, phi x y z equal to 0, x y z equal to constant is the equation of a surface. So when this is equation of a surface, if you take a gradient of phi, then that will give you the normal. So normal vector to this quantity will be grad of x square plus y square. So you take x square plus grad of x square plus y square gradient. So there should not be any dot product here. So there is a typing mistake, no dot here. Okay, please don't mind. There should not be a dot here in the gradient operation. This is a vector operator and this is color. So there should not be any dot here. So that was a typing mistake. And when you take a grad here, this will be like you have to differentiate this with respect to x. So when differentiating this quantity with respect to x, differentiation of x square is 2x, differentiation of y square is 0. So therefore I cap coefficient will be 2x. And here differentiation of this term with respect to y, differentiation of x square is 0, differentiation of y square is 2y. So 2y into j cap, the second term. Now if you differentiate this term with respect to z, differentiation of x with z is 0, y with z is 0, because x and y and z are independent coordinates. So if you differentiate one coordinate variable with another coordinate variable, they are independent. So it is 0, right? So this is the vector. So once you have a vector, in order to find unit vector, like if you have any vector a here, if you want to find unit vector, what you have to do is simply divide that vector with the magnitude of that vector. Then you get a unit vector along that a direction, right? This is how we get a unit vector. Just divide the vector with the magnitude of that vector. Then you get that unit vector along that vector direction. So this is what we do. In order to find unit vector, divide the vector with the magnitude of the vector, and this is the vector, and the magnitude is square root of 2x to the power square. So that means 2 square x square. 2 square is 4, 2 square is 4, and then this is what you get. I hope this is okay with you. Now this is your unit vector. So this unit vector at this point, what the unit outward vector is, given by this expression. All right. So at another point over here, the unit outward vector is given by this. The unit outward vector for different point on the curved surface will be different, because the unit outward vector is from vector field, or it depends on the x and y value. So at one point, the unit outward vector may be pointing outward in this direction. At another point, the unit outward vector will be pointing in this direction, depending on the x and y values here. Right. So here, what we have to do here is that we have to perform vector A with ds3 surface element and this unit vector. So you're going to do this product A dot n. So the vector field, we know it. This is the given vector field, and unit vector, as we deduce, it is this. And if you take the product, this is what we are going to get. Okay, now I think the rest of the calculation will simply follow. So if you take this A dot n, we already obtained A dot n as this quantity, that is A dot n is 2x square minus y cube. A dot n is 2x square minus y cube. So 2x square minus y cube, you just put x as 2 cos theta and y as r sine theta, as sorry, radius is 2, so y is 2 sine theta, so like the substitution I discussed. So you just substitute here, and this is algebraic simplification. This is what you will get after this thing, 2 square into 4, 2, and you take 8 as a common, it becomes 16, and this is what you have. And cos square theta, using trigonometry, it is 1 plus cos 2 theta upon 2, and sine cube theta, instead of sine cube theta, you simply write sine square theta into sine theta. So sine square theta is 1 minus cos square theta. So I think you can carefully follow this trigonometric simplification. So here you see that the integration is with respect to the area element is 2 d theta dz, as I discussed, and you have to integrate with d theta first, and then you perform the integration with z. Then if you perform this integration, finally you will get this as 48 pi. So on the right hand side here, you see that we have to the right hand side, the total flux is flux over the surface S1, this bottom surface, flux over the surface S2, the top surface, flux over the curved surface. So you have to sum all of this. The bottom surface flux is 0, the top surface flux is 36 pi, and the curved surface flux is 48 pi. So if you do the summation, this is 84 pi, which is same as what you have already calculated for the left hand side here. The left hand side, if you calculate the volume integration of divergence, this is what you get, 84 pi. Okay, so this is, I think, probably understandable to you. So you follow my lecture again. If you have any problem, any doubt in any of the mathematical steps, you are feel free to ask me to WhatsApp. It's not a problem. Now I think we can go to Stokes theorem. Stokes theorem is for a open surface. See, in this divergence theorem, we are considering a closed surface. We are considering a closed volume, which is bounded by a closed surface. The surface could be spherical, so it could be cylindrical, or it could be any surface, but we are considering a closed surface here in the divergence theorem. But in the Stokes theorem, we are going to consider an open surface. Almost sneezing. So here, what it says here is that if you consider any open surface, two-sided open surface bounded by a closed non-intersecting curve. So non-intersecting curve is what you call a simple closed curve. Like you can consider something like this. So if this is an open surface, this is a curve C, and this curve is like this curve is surrounding a surface S, or you can consider something like this, uh, let's say this is a curved surface. This is a curved surface, sorry, this is a curve, see, a complete a closed curve. So this is a closed curve, and the surface bounded maybe something like this. So I hope you can see the picture. This is, I don't know if I can show you some other thing. Anyway, I think with an example, it will be more clear to you, the surface. So if you have any open two-sided surface, it may not be a flat surface. It can be a curved surface bounded by a simple non-intersecting closed curve. Then if A is a vector field which has a continuous derivative within this surface, then Stokes' theorem says that line integration of the vector field over the closed curve. So counterclockwise means, clockwise, you know it, it is rotating like this. Counterclockwise means it is rotating like this. So loop integration of the vector field, line integration of the vector field along that such kind of simple closed curve. If you integrate vector field around this, if you perform vector field integration around this closed curve, then that equals surface integration of the curl of the vector field A. Surface integration of the curl of the vector field A. Curl of the vector field means it measures a rotation of the vector field. So this is the total rotating flux, okay, across the surface, which equals what is that? Line integration of this vector field around this closed curve. This is what Stokes' theorem says. So I think this will be clear to you if you look at this surface. Here, the question here is to verify Stokes' theorem for this particular vector field, and where S, the surface under consideration, is the upper half of the sphere given by this. This is the equation of a sphere, x square plus y square plus z square equal to 1. This is a sphere of radius 1, right? This is a sphere of radius 1. X square plus y square plus z square equal to 1 is sphere of radius 1. So S is the upper half of the sphere, means something like this. See, upper half of the sphere S, this is something like this, and C is its boundary. So the boundary here is, the boundary of this surface here is a circle on the xy plane. The boundary here is a circle on xy plane. Okay, so what is the equation of this circle? The equation of this circle is going to be x square plus y square equal to 1. So because on xy plane z is 0, right? So the equation of the circle on xy plane, or the curve which is the boundary of the surface under consideration, is a circle of radius 1, x square plus y square equal to 1. All right, so here you find that unit vector k cap is pointing along the z-axis, and unit outward vector, whenever we consider surface element over here, ds, ds vector will be ds into unit outward vector. N cap is unit outward vector. Unit outward vector means a unit vector or a vector having unit magnitude pointing away from the surface, So if you consider ds vector here, ds element, surface element over here, unit outward vector will be something like this. Unit vector which is pointing outward from the unit normal vector. In fact, this is unit normal vector. Normal means this vector is at 90 degree to the surface here. All right. Now, so the boundary of surface as a circular radius, this I have discussed, right? So what is the line element? Line element in general, line element dr here over here, what you have to do is, in order to serve like integrate over this curve C here, you have to consider a line element dr. So dr vector is in general, this is dxi, dyj, dz, k. Okay, because r vector, position vector, we write it as xi plus yj in Cartesian system. This is your r vector. So dr vector will be dxi dyj plus dzk. So as simple as that. Now you can consider this, and now you take the a dot dr, because you are going to execute left hand side is a dot dr vector, this along the curve. This is the left hand side of your Stokes theorem. So you take a dot product of a with your dr vector. Okay, and also you should know that over here, as I said here, as you perform this loop integration, a dot dr, you have to perform this loop integration along this line, along this curve, which is bounding the surface under consideration. So along this curve, since as I have said here, a curve, the curve under consideration is lying on the xy plane. So along this curve, z value is 0, right? So because of that, when you, after taking the a dot dr, you just put z as 0 along the curve, z value is 0, right? So if z is 0, a dot dr reduced to this, and you just use in terms of theta, x as r cos theta, and here your radius is 1, so xy as r sin theta, your radius is 1. Then this integration of a dot dr along the circle on the xy plane will be reduced to this. Okay, and because your line element here, your line element, where is that? Yeah, this will reduce to that. A dot dr over here reduces to this, right? A dot dr reduces to this. So this is dx. X is r cos theta, means x is r cos theta, means your dx is r, differentiation of cos theta is minus of sine theta d theta. Okay, so dx will be minus of r sine theta d theta. Your r is 1, means your dx is minus of sine theta d theta. So if you just put that over here, we perform the remaining integration. So this is a simple, I think, trigonometric calculus. So you just perform the integration of this 2 sine theta cos theta is sine 2 theta. So use your trigonometry knowledge and your calculus knowledge to perform the integration. So sine 2 theta integration equals cos 2 theta upon 2, like that. So if you continue, eventually you will get pi, right? And just a minute here. Okay. So here on the right hand side of this Stokes theorem is surface integration of curl of A. So you have to perform the curl of A. Curl of A is this. This is how we perform curl of A. I've given you an example also. Curl of A is this I have explained. So you perform the curl of A, eventually you will get k cap. So this should not be a problem. So I cap coefficient will be differentiation of y square minus of y square z with respect to y, that is minus of 2yz, minus differentiation of this quantity with respect to z, that will be minus of 2yz. So minus and minus cancels out plus. So like that, if you do that, this is what you're going to get, curl of A. And here this will be curl of A dot n cap ds, and you know that this curl of A is k cap. You have calculated this curl of A as k cap, right? So here this will be k cap dot n cap ds. So this will be simply a projection of n ds vector on the xy plane. Okay, so what I mean by the projection here is that, say this is k cap is along the x-axis, and let's say if you consider any surface element here, this is your n cap. So n cap dot k cap will be, this is theta, so n cap dot k cap will be cos theta, because the magnitude of both n cap and k cap are 1, so cos theta. So if you have a surface ds here, so what you're going to have here is that ds ds n cap dot k cap will result in cos theta ds. So if you have a surface ds over here, cos theta ds will be a projection of this surface on the xy plane, a projection of this surface on the xy plane. So this will be your ds cos theta. So it's something like this. Just a minute, let me. So let's say you have a vector a here, and let's say you have this exists as your y-axis, so this is j cap. So if you perform a dot j cap, a vector dot j cap, this will be magnitude of a, and j cap magnitude is 1, and cosine of the angle between them, this is your cos theta. So magnitude of j cap is 1, so this is magnitude of a cos theta. What is this magnitude of a cos theta? This will be, if you drop a perpendicular here, this segment, this is your projection here, this is the magnitude of a cos theta, right? So similar to that, if you define something like this, this is, let's say, your x, this is, let's say, your y, this is, let's say, your z, and let's say you have a certain surface, for example, surface which is a little bit inclined, something like this, okay, whatever may be the surface. So this is your ds, and when you write your ds vector, this is the magnitude upon n cap, this is the direction of n cap, right? So along this z-axis, the direction unit vector is k cap here. So if you take a dot product here, what is that? K cap with ds vector, this will be k cap dot ds n cap, and if the angle between them is theta here, this is going to result in k cap dot n cap will be magnitude of both of these vectors are 1, so the angle between them is theta means cos theta, right? So it will result in ds cos theta. So what is ds cos theta? If this is your ds here, ds cos theta will be projection of this surface on your xy plane. Okay, projection of this surface on your xy plane is your ds cos theta. Okay, so if that is the case, then on the xy plane, the area element will be dx dy. Okay, on the xy plane, you have your area element ds. On the xy plane, the projection of ds on the xy plane will be, the element will be dx dy, because I think I have convinced you that on the xy plane, like when we consider z equal to 0 plane and z equal to 3 plane, so we have discussed that the real element on such plane, that is xy plane or any plane parallel to the xy plane, the real element will be dx dy. That was what I have discussed before. So if you recall that, we can write this as a dx dy, and now since the surface the surface has to be performed, integration has to be performed over this now, because this is on the xy plane now. So instead of having the whole x squared plus y squared plus z squared equal to 1, we have projected our surface on the xy plane because of the dot product with k cap here. So we have to follow this, right? So in this surface integration, instead of this, we write dx dy, and here the limit will have to be chosen according to this, which says that y square is equal to 1 minus x square, or y is equal to square root of plus or minus 1 minus x square. So you perform the integration from minus square root of this to the plus of this, and then you have to perform x from the radius, the back side of the radius, that is x equal to minus 1, x equal to 1. So you perform that integration, And if you do that, say, uh, moreover, whatever function you're having here, it is constant, right? So you can consider this as an odd function. So this integration from this to this, like minus a to a, can be written as 2 times 0 to a, so 2 times y equal to 0 to this. So you perform that integration, and this is what you have. And then after that, you have this. So this is again an even function. If this is an even function, if you just put f of minus x here, minus x square is this, and same as f of x. So even function means minus 1 to plus 1, you just convert into 0 to 1, so 2 2. And eventually, if you put using simplify this integration using this calculus, that is, sorry, trigonometric property, you will eventually find this as pi. Okay, so this will be exactly same as that. So that's how we do it. So I will provide you the notes also. Anyway, so quickly I will go through this. I think how much time we have spent. Yeah, we have spent around 35 minutes. Only for a few more minutes. So this is another vector integration theorem. So this is called Green's theorem. So as I said before, in Stokes theorem, we are considering an open surface, which may be flat or which may be curved also. As we just discussed, we are considering a sphere which is cut into half. So that was a curved surface bounded by a circle on the xy plane. That was what we discussed in the case of Stokes theorem. So we are considering some sort of curved surface bounded by a curve, right? So, but Green's theorem is valid on only for plane. So here we are considering R as any region on the xy plane, right? So this is, let's say, x axis, let's say this is your y axis. So you consider any region R, flat region R on the xy plane, right? On the xy plane means this is flat plane, flat surface, bounded by a simple closed curve C, right? So then what it says is that then if m and n are continuous functions of x and y having continuous derivatives within this region R, then Green's theorem says that loop integration, so loop integration, there has to be a symbol like this, loop integration of m dx plus n dy equals surface integration over this region, that is surface integration over this region, del n upon del x minus del m upon del y, where C is the loop which traverses in the counterclockwise direction. So counterclockwise direction, C is counterclockwise. It is rotating like this, counterclockwise. So here again, the surface element here is written as dx dy, because we are considering a region on the xy plane. So any infinitesimally small surface over this can be represented using small segment along x multiplied with small segment along y. So dx dy. Okay. So let's quickly go through this, and then we can stop. I think I can finish this in about 5 minutes, because I think once you follow the previous two calculations, this should not be a problem. So verify Green's theorem for this, where C is the closed curve of the region bounded by y equal to x and y equal to x square. So y equal to x is what is y equal to x? Let's say this is your x axis, this is your y axis. Y equal to x is just a straight line like this. So for like if x is 2, y is also 2, so it is y equal to x. If x is 4, y is also 4. If x is 5, y is also 5. So this is y equal to x. If x is 6, y is also 6, like this. All right, so it will be a straight line like that. Now and here, when you consider y equal to x means y equal to x as equation of a line, then this angle will be at 45 degree. Because x value is always equal to y, that means this angle will be at 45 degree here. All right. Now you have another curve, another line here. This y equal to x is extending up to this, something like this. Y equal to x. The equation y equal to x, sorry, the line y equal to x will be extended from this infinity up to infinity, right? Now, what is y equal to x square? Y equal to x square here at x equal to 0, y value is 0, x equal to 0 0.1, y value is x square means 0 0.1 square, this will be 0 0.01, x equal to 0 0.2, y value is 0 0.2 square means 2 to the power 2 is 4.04. So when x value is 0 0.9, y value will be 0 0.9 square, that it will be 9 times 9 will be what is that, 81, right? So 81, so there is a decimal point, this will be 0.81. But when x is 1, y will be 1 square will be 1. When x is 2, y will be 2 square, that is 4. When x is 3, y will be 3 square, that will be 9. So if you follow that, this will represent something like this. This will represent, let's say this is your x, y, and let's say you start with this here. This will represent something like this. This is, let's say, 1. This is, let's say, 1. So this was your y equal to x line. Now y equal to x square line will follow something like this. It will follow something like this. When x value is this is 1, x value is less than 1. When x value is less than 1, if you see that x equal to 0.1, y is 0.01, 0.2, 0.04, 0.9, 0.81. So when x value is less than 1, then in that case, y value will be less than x. But when x value is greater than 1, y value becomes x equal to 2 means y is 4, x equal to 3 means y is 9. So your line, your curve will be this. This is y equal to x square. I hope you can picture that. Now, we are considering a region bounded by these two lines. So this is one line, y equal to x. This is another curve, y equal to x square. So the region bounded by these two will be this region. This is the region under consideration here for our problem. Okay. So this is the region we are going to consider R, and we are going to consider counterclockwise. Right, counterclockwise means rotating in the anti-clockwise direction. So we have to perform the integration from this to this along this line and then come back to this point. So that is the loop integration that we are going to consider here. Okay, the loop integration, this loop integration has to go in the counterclockwise direction. All right. So just 1 minute. I almost finished. Just 1 minute, I have to forward one message. Okay, so this is m. In this case, n will be x squared, so you can just write it like that, and you have to perform the integration over this closed loop, almost over. Okay, so I will not take much time now. So we can divide into two segments, one along this curve. This curve is defined, the curve which is defined by y equal to x squared. Along the curve defined by y equal to x squared, we write it as c1 curve. And we can divide another curve along which we have to integrate is along another line, is from this point to this point. From this point to this point, it will travel along y equal to x, right? It will travel along y equal to x line. So the complete loop integration, that is c here, is can be divided into two segments, one c1, from this to this, another c2, right? So as you travel along from this point to this point along y equal to x squared, the limit, the x value will change from 0 to 1, and from this to this you are coming back, x value will go from 1 to 0, like this. Okay, because here along c1 you are going to write, along c1 the equation of the curve is y is x squared, y is equal to x squared, and the x limit goes from 0 to 1. So for m you just put for m in place of y you just put x squared, in place of y you just put x squared. So this is what you are going to get. All right, so your dy also here in this case, y equal to x squared means your dy will be 2x dx. Okay, 2x dx. So if you perform this simple integration, you should be able to arrive at this. Okay, so perform the integration. This is what you're going to get, and I think just simple integration with the limit. This is finally what you're going to get. Now along C2, first we are traveling along your C1 here. This is your C1, that is the equation here is y equal to x squared, and we have arrived at this point. From this we are traveling back to this along this line. So the equation of this line is y equal to x. So yeah, along this line, instead of y you just put x, instead of y you just put x. This is what we're going to get. The integration limit is from 1 to 0. So if you do that, this is what you're going to get. And yeah, the whole integration will be here, out here you get -1. This will be 19 upon 20 minus 1. So this is what you will get. Now integration over the region. Just 1 minute, just 1 minute. What is that? Oh, collaboration with Pachhunga University. Resource collaboration. Resource collaboration with Uzbek University. DST sponsored project. Okay, I hope that answers his question. Now integration over the region. So again, the right hand side is simple. N value you know, M value you know for a given problem. So you just differentiate. N value is x squared, M value is this. So you just differentiate. This is what you're going to get. And if you do this, then this is what you're going to get. And here dx dy. So you have to integrate along this line for the y and x value going from 0 to 1. So simply you will get this result. Okay, so if you perform that, the reason here we are going to integrate over this is that say you are going to perform integration with x and y, and what we are having here is that this exists is y, this is your x exists, and this curve is defined by y equal to x squared, and this line is defined by y equal to x. So you just take a limit of y from this y equal to x squared to y equal to x. So along this line, and you travel x from 0 to 1. This is 1 1, x value is 1. You travel x from 0 to 1, so that way you can perform integration over this region. Okay, if you do that, you will get the same thing, and that verifies your Green's theorem. So this is your assignment. You can calculate this. All right, I will stop. So I will upload this video once I reduce the size. So if you type your attendance, you can exit the meeting. No more class this week, so hopefully I can take 2 more class next week, and there we can start curvilinear coordinates. Okay, good night everyone. Type your attendance and exit the meeting. All right, I think I can exit the meeting now. Everyone has type attendance.